So at this point in the course, we've probably trained you to use the words infimum and supremum instead of minimum and maximum. But in this short video, we're going to find some new situations where you get to use minimum and maximum again. So here's the theorem. I'm going to fix a compact set k and a continuous function f from k to the real lines. Then there exist 2 points, which I'll call x min and x max, so that f of x min is less than or equal to f of x, which is less than or equal to f of x max for all x in k. Now, unless k is empty or otherwise sort of degenerate, what that really means is that this point here is the infimum of f of k, and this point here is the supremum of f of k. And the sort of exciting content of the theorem is that, of course, there's always going to exist some sequence so that f of xn is converging to the infimum. But here we've actually seen that sequence actually has a nice limit, and so we actually achieve the infimum, and similarly we achieve the supremum. So what's the proof of this? Well, we've seen already that f of k is compact, and so by Honey-Borel, f of k is bounded. And so in particular, we actually have a supremum which is finite. So I'm going to let fm be the supremum of k. Now, what does it mean for m to be the supremum? Well, one thing that it means is that you can get very, very close to the supremum while sitting inside of f of k. So in particular, there exists a sequence yn sitting inside of f of k, so that yn is bigger than or equal to m minus 1 over n. So yn is going to be getting very, very close to m. Now, of course, yn is in the image of k, and so there exists a sequence xn, so that yn is equal to f of xn. Right? Again, we can't take x to be f inverse of y, but nonetheless there exists at least one xn, so that yn is equal to f of xn. All right, taking stock and decoding what we've just said, we've just seen that we have a sequence xn, so that m minus 1 over n is strictly less than f of xn, and of course, m is the supremum of f of k, so we also get that f of xn is less than or equal to n. Now it's clear that this sequence, well, is just m, and this sequence m minus 1 over n is converging to m, and so by the squeeze theorem, f of xn is converging to m. We're almost done, except of course there's nothing telling us that xn is a nice convergent sequence, right? We just know that f of xn is a convergent sequence. This is where we use the fact that k is compact in sort of a serious way. Since xn is sitting inside of k and k is compact, and in particular sequentially compact, there exists some subsequence, which I'll denote x sub n sub m, so that x sub n sub m converges to something, which I'll call x, which lives inside of k. Okay, so this is the place where we really use compactness in sort of a more serious way. All right, at this point we have a nice convergent sequence x sub n sub n, x sub n sub m, and we know that when we take the image, we get this sort of maximizer, and so we just use sort of the same calculation we often do when dealing with limits and continuity. We have f of x is equal to the f of the limit as m goes to infinity of x sub n sub m. Well, that's just what the definition of x is. The next step, we interchange the limit and the function. So f of the limit is equal to the limit of the functions. That's what we sort of usually do when we're dealing with continuity. And of course, we've already checked that f sub x sub n is converging to m, and therefore the subsequence f of x and m is also going to be converging to the same value. So at the end, what have we gotten? We've gotten that f of x is actually equal to m for some x in k. So that x is going to be what I called x max in the statement of the theorem. I'm not going to prove the same thing for the infimum. The proof, of course, is essentially identical, and indeed, you could use the fact for the supremum for the function minus f to get the existence of x min. All right. So what can we use this theorem to do? Well, there's sort of a nice corollary. If f is a continuous function from a compact interval ab, then in fact the image of f is itself another compact interval cd. All right, how do we prove something along those lines? Well, the first step, of course, is sort of clear. I'm going to let c be f of x min and d equal to f of x max, where x min and f and x max were the things that I had in the previous theorem. Okay, so what does that look like? Oops. I have some interval ab, and I have some point x min and f of x min here, and some point x max and f of x max there. And this interval here is going to be the interval from c to d. All right, So what do we know about this interval? Well, certainly f of the interval AB is contained in the interval from C to D, right? Because C is the infimum and D is the supremum. So that part's clear. Then we have this second fact which we got from the previous theorem, which is that actually the point C and D itself is sitting inside of the interval f of AB. So that part's not so obvious, right? That actually the endpoints are really sitting inside of the image, but we know that that's true. So by the intermediate value theorem, for every point E that's sitting between E and D, for all E between C and E and D, there exists some Z in A, B, actually, some Z between A and B, such that f of Z is equal to E. Right? That's what the intermediate value theorem says. For every E between C and D, there exists some Z so that f of Z is equal to E. So in particular, if the points C and D are both in the image f of AB, then in fact the entire interval from C to D must also be sitting inside of the image. So what have we shown? We've shown the interval is sitting inside of the image. We've seen that the image is sitting inside of the interval. And so in fact, if we have these containments in both directions, then the image f of AB must be exactly equal to the image CD. I'm going to close out with one last warning. At the end of two videos ago, we saw a few examples where we were looking at the continuous image of compact sets, and we pointed out that actually if the set that you're interested in isn't compact but it's closed or it's bounded, those two assumptions by themselves, closedness or boundedness, they don't really buy you anything. You really need compactness to get any of these sorts of theorems to be true, and it's worth revisiting those examples in the context of the current video. All right, that's